Hello everybody, my name is Kazem Cheshmi from the University of Toronto and I'm going to present NASOQ, a numerically accurate sparsity oriented QP solver. This work is done in collaboration with Danny Kaufman and Shoaib Kamil from Adobe Research and Maya Mehdi Dehnavi from the University of Toronto. Solving quadratic programming problems or QPs is critical in almost every computational field and discipline. Unfortunately, existing QP solvers often fail as problem types and requested accuracies change. Today, I will present our work on a new QP algorithm, NASOQ, which enables reliable and efficient solutions of sparse QPs across problem types, scales, and accuracies. NASOQ is available as open source and can be used to solve equality and inequality QPs. Before explaining NASOQ, let me give a brief overview of what a QP is. A QP problem minimizes a quadratic objective subject to two kinds of linear constraints: equality constraints expressed as ax equal with b, and inequality constraints given as cx less than equal with d. In other words, a quadratic program is just a generalized linear system solved, but with added constraints. Here we focus on problems where the matrices in the QP H, A, and C are often sparse and large. Similar to linear solvers, we need QP solvers that are accurate, efficient, and scalable. By accurate, we mean that the provided QP solution by the solver has an error less than a user-requested threshold. For example, the solution should not violate the requested accuracy in any constraint. By efficient, we mean that the solver is fast to provide an accurate solution. And scalable means that the solver efficiently provides an accurate solution across large and small QP instances. The key challenge for solving a QP is in identifying an active set. An active set is a subset of a QP's linear inequality constraints that are treated as equalities at optimality. Let's use an example to explain the active set. The objective f in the example is a quadratic function shown with green circles. The problem has 5 linear inequality constraints. The lines in the graph are half spaces corresponding to constraints. The blue region in the graph represents the overlap between linear constraints, which is the feasible region. The active set is used to determine the constraints to be considered or the constraints that can be safely ignored to find the minimum of the objective function. As you can see in this example, the first and the third constraints shown with green need to be in the active set to find the minimum of the objective, which is in point 1, 1. Once we know the active set, the QP is solved by ignoring all other constraints and keeping the active ones as equalities. Algorithms for solving larger-scale QPs often treat the entire constraint set as approximately active with penalty terms on all constraints simultaneously. This allows the application of large-scale general-purpose sparse linear solvers, but generally comes at the cost of uncertainty in the active set and degraded solution accuracy. On the other hand, to address accuracy, many other QP algorithms use active set methods. These are a range of methods that iteratively explore and test active set proposals. Details vary across methods, but in all cases, each iteration requires solving a large number of reduced QPs. The 3 reduced QPs for solving our QP example are shown here. Each reduced QP is solved subject to a different set of proposed active constraints treated as equalities. In turn, solving these many reduced QPs accurately and efficiently is the computational crux of active set methods. This amounts to solving at each instance an indefinite linear system for equality constraint optimality conditions. The 3 linear systems corresponding to the 3 reduced QPs are shown here. As you can see, each indefinite system is different from the previous one by 1 row or column. The different row is shown with blue in each linear system. We built NASOQ, a QP solver that solves the scalability issue of active set methods by taking advantage of small changes in indefinite linear systems of consecutive reduced QPs. NASOQ provides accurate and scalable solutions to QP instances efficiently across scales. To do so, NASOQ is built on two key contributions which I will introduce next. First, a sparsity-oriented row modification that we call SOMOD, and second, a load balance block LDL solver that we call LBL. SOMOD reuses computations from the linear solve of the previous iteration to find the solution of the current linear system. Before diving into how NASOQ uses SOMOD, let's review accuracy measures for QPs. These are given by the optimality conditions for solution of a QP problem and are a bit more complex than those for a linear system. The first is primal feasibility accuracy. This ensures linear constraints are satisfied. The second is the stationary accuracy. This measures the balance between energy and constraint gradients. Variables y and z are dual variables, and x is the primal solution. The third is complementarity accuracy. Here we are measuring the pairwise products of dual variables and their corresponding inequality constraints, and it is critical for correctly capturing active sets. The fourth is non-negativity accuracy, and this condition ensures that dual variables are positive. NASOQ ensures that the user-requested accuracies for all these measures are satisfied. Let's now look at SOMOD in more depth. As I mentioned, we designed SOMOD to solve the successive indefinite systems called KKT systems that are required at each active set iteration. SOMOD has two steps: initialization and factor modification. In the initialization phase, SOMOD benefits from the fact that the sparsity pattern of constraints in the QP problem is known ahead of time and uses that sparsity information for fast row modification in the second phase. In the factor modification step, a linear system is solved after removing or adding a row to the linear system. Next, I will explain how SOMOD is used in the NASOQ algorithm and then illustrate the details of SOMOD via an example. NASOQ is based on an active set algorithm called the Goldfarb-Idnani method. As shown here, similar to other active set methods, the algorithm first finds an initial guess in the feasibility phase. The feasibility phase ensures the initial guess is feasible, which for the Goldfarb-Idnani algorithm means all dual variables should be non-negative. As you can see, the SOMOD initialization phase is used to determine the initial guess for dual and primal variables. Then the algorithm in the optimality phase iteratively improves the current solution by solving KKT systems while preserving the feasibility condition. NASOQ uses the SOMOD factor modification to update the current solution. In each iteration of the optimality phase, the solution is updated with step direction vectors alpha, pi, and mu, and the scalar step length t. Similarly, the active set is updated in each iteration based on the step information. To explain details of SOMOD, let's solve a QP instance using the NASOQ algorithm. The input matrices and vectors to NASOQ are shown in this slide. Let us start with the initialization phase. The initialization phase of SOMOD starts with creating an inclusive matrix from the sparsity pattern of the objective and constraints matrices which are inputs to the QP problem. The inclusive matrix includes the structure as if all constraints are active. The inclusive matrix is then permuted with a field-reducing permutation to compute the sparsity pattern of the L factor with minimum number of fill-ins. Fill-ins are additional non-zeros created in the factor during a matrix factorization. Then, the L factor is converted to a supernodal L factor by grouping columns in a supernode. A supernode is a block of columns in the L factor that have similar sparsity pattern where pattern doesn't have to be exactly the same. Boundaries of supernodes are shown with purple lines. Then the inclusive assembly tree is computed. This tree represents the dependence amongst computations or supernodes during factorization. The color nodes correspond to the inequality constraint rows. These caller nodes are then removed to create the prune-inclusive tree that will be used for the initialization, as I will explain. Similarly, the SOMOD initialization phase hides columns of the L factor corresponding to the inequality constraints, so it does not get involved as long as constraints are not activated. SOMOD uses the prune assembly tree and the sparsity pattern of the L factor to finalize its initialization phase by computing numerical values of the L factor. To find values of the L factor, we build a new indefinite factorization algorithm we call LBL, which is Load Balance Block LDL Solver. LBL skips the hidden columns during factorization and enables the application of row modification in the following steps. LBL can also be used as an efficient, high-performance indefinite direct solver on its own for other possible applications. After the factorization is done, SOMOD computes x0 and y0 by solving the system shown here. The active set W is also set to null initially. After the initialization phase of SOMOD, the factor modification phase begins, in which a KKT system in each iteration of the NASOQ optimality phase is solved. SOMOD factor modification uses the information of the last solve, which are the prune assembly tree and the modified L factor, to efficiently solve the KKT system of each iteration. For example, in the first iteration of our running example, NASOQ solves a similar linear system for a different right-hand side. The right-hand side is the most violated constraint based on the current solution, which is the constraint tree. The step information alpha, pi, mu, and t are then used to update the dual and primal variables and also the active set. The new KKT system that NASOQ solves in the second iteration includes constraint tree that was activated in the previous iteration. As shown, the corresponding column to constraint tree is visible in supernode number 10 of the L factor, and its corresponding node is also added to the assembly tree. This time, the most violated constraint is constraint 1, which is in the right-hand side. After this step, all constraints are satisfied and thus the QP is solved. As you can see, NASOQ reuses computations with the help of SOMOD. Please see our paper and code for more details on how NASOQ functions. Next, I will discuss results using NASOQ. To evaluate our solver and compare it with other solvers, we built an extensive repository of sparse QP problems from a range of real applications. As shown, the dataset repository includes a wide range of problems that vary in number of variables and constraints, with the number of non-zeros ranging from hundreds to millions. For comparison, we select to our knowledge the most robust and performant available QP solvers out there. Specifically, we compare NASOQ to industrial libraries such as Groby and Mosaic and the state-of-the-art open-source QP solver OSQP. We evaluate all solvers with respect to their failure rate and so accuracy across all problems in the benchmark and their corresponding speed. I should mention NASOQ has two variants, fixed and tuned. Please see our paper and code for details. NASOQ fixed provides fast convergent behavior at the cost of a slightly less accuracy, while NASOQ tuned can be a bit slower while offering best convergence thus far. Our paper includes a complete analysis across a wide range of accuracies. Here I'm demonstrating results for a requested accuracy of E-6 for all measures. The results show NASOQ tune has no failure across problems, while NASOQ fix has the lowest failure rate after NASOQ tune. The results also show that, along with the greatly improved reliability, NASOQ is on average the fastest solver across the entire benchmark set. Again, please see our paper and repository for details. Our work proposes NASOQ, which is an accurate, efficient, and scalable solver for QPs. In addition, for NASOQ, we have developed LBL, an efficient parallel indefinite direct solver for symmetric linear systems that can be used both within NASOQ or as a standalone solver. NASOQ currently outperforms existing solvers on all three metrics across a wide range of problem types. NASOQ, along with LBL and our full QP benchmark repository, is available in NASOQ open source project. Looking ahead, as we continue to improve NASOQ, we hope to hear from you on the application of NASOQ for your QP problems and welcome new QP problems to be added to our benchmark. Thank you.